Okay, let's start. Thanks everyone for coming. It's glad to see so many people, despite the long list of seminars we have been watching and attending the last few days. So I'm glad to introduce the first speaker of today. Toshiya Iwata is a graduate student at the University of Tokyo with a strong interest in black hole accretion and X-ray emission from these systems. He's worked on the timing analysis of the iron emission line from the radio galaxies in HAWC, and that's also contributed to developing the X-ray polarimeter using 5-pixel MOS image sensors. Currently is developing Monte Carlo radiative transfer code that incorporates general relativity to study X-ray spectrum and polarization from black hole accretion flows. Today is going to talk us about Monte Carlo simulations near black holes, develop a general relativistic radiative transfer code. Is visiting also for a few more days, I think, right? A few weeks, and is yes of takes time. So please take the floor for the minutes. Thank you.
Hello everyone. Thank you for introduction. Thank you for giving me a chance to talk today. I am Toshiya Iwata, a graduate student at the University of Tokyo. First, I'd like to briefly introduce myself. As I mentioned, my name is Toshiya Iwata, and I'm a graduate student at the University of Tokyo. And I have studied there since 2021 under the supervision of Professor Ayabamba. My research focuses on X-ray astronomy, and I have worked on several projects. And first, I conducted the timing analysis of iron emission line from the radio galaxies in Taurus A or A. And the result of this study is which has been published in our paper. And also, I am a member of the Crescent PV target team working on CNA. I also involved in development of X-ray polarization using a fine pixel CMOS sensor. And this study was a main topic of my master's thesis and also published in our paper. And currently, I am working on a development of MonacoGR, a Monte Carlo radiative transfer code incorporates the general relativistic effect. So today I will briefly introduce my work on CNA and X-ray polarimetry, and I'd like to talk about the motivation and current status of the development of MonacoGR. So first, CNA is one of the best targets to study the structure around the supermassive black hole in radio galaxies because it has been observed repeatedly in X-ray energy band. And the ion line was detected at 6.44 keV. And it is believed that ion line is emitted from the reflector irradiated by the central X-ray source, but the exact origin is still open question. The ion line could come from broader region, torus, or more distant object. So our goal is to reveal the origin of ion line, and as this figure shows, the iron line, the light travel distance of the iron line is longer than the direct component that is directly comes from X-ray source. So we can, so the flux variation of the X-ray source, flux variation of the iron line lag behind the flux variation of the direct components. So to use this feature, we compare the light curves of the direct component and the iron line. And we found that interesting features. The first, the iron line flux dropped significantly between 2013 and 2015. And this indicates the existence of short distance components that can respond to the flux change of the X-ray source left behind about 1 year or shorter. But on the other hand, the flux variation of ion line is smaller than that of the direct components. So it indicates the presence of a long-distance component that acts to smooth out the variation over time. So from these features, it seems that both this short distance and long distance components around the central X-ray source. So to study further, we use the transfer function approach. The transfer function is how the flux of ion line respond to the radiative flux. The right curve of the ion line can written as a convolution of the transfer function and the light curve of the direct component. And based on the features of the light curve I shown in this previous slide, we assume the double top-cut function, and that contains the both short lag and long distance components. Although the double top-hat function represents the situation with the two spherical shells around the central X-ray source, but we did not consider it as actual real physical structure of the system. Instead, we use it as a kind of approximation of the system. And by feeding the convolution to the ion line data we estimated the parameters for short distance and long distance components. And the results indicates that the ion line likely to come from the torus or torus along with the more distant objects. For more details, please refer to my paper. And now we have PRISM, which has a energy resolution of 5 eV. So thanks to this high resolution, it is expected that we can constrain the emission region from the line profile of ion line. And the PV data have been already obtained, and now our analysis is in progress. So, and I think the result may be published soon. So please stay tuned. Okay, let's move on to the next topic. Next topic is the X-ray parameter using a CMOS image sensor. First, I'd like to introduce one of the scientific motivations of the X-ray polarimetry. In black hole accretion system, where the gas accreting on the black hole, HAWC believed to be originated from the hot medium around the black hole called corona. But the exact structure and the location of the corona is still uncertain. And the several models was proposed, as the figure shows. But the system is very complex, so it is impossible to spatially resolve these structures with today's current X-ray observatories. But X-ray polarization depends on the geometrical structure of the corona. So X-ray parameter will help us to constrain the geometrical structure of them. And it will also help us to determine the origin of the corona, and also important for to measure the black hole spin using the reflection spectrum of the black hole. And X-ray parameter is hard to realize because of the technical reasons, but December 2021, the XP was finally launched, and X-ray imaging parametry was started. An energy band of 2 to 8 keV. And our project, we call CfA, try to realize the hard X-ray imaging parametry using a fine pixel CMOS sensor. Compared to the XPE, our instrument will have coverage of high energy band and also better energy resolution thanks to the silicon detectors. So I'd like to explain how CMOS sensor work as a polarimeter. The basic principle is the same as the XPE. We use photoelectron emitted and this detector. So when the X-ray interact with the detector, the photoelectron emitted and the emission angle is related to the the polarization direction of the incident photon. The angle follows this equation. So by tracking the photoelectron with the fine pixel sensor and by estimating the photoelectron emission angle for each event, we can determine the polarization direction and the polarization degree from the distribution of the angle. So to check if actually a CMOS sensor can use as a polarimetry, we evaluate the polarization sensitivity of our CMOS sensor. The polarization sensitivity of the polarimeter often expressed as MDP99, which stands for minimum detectable polarization on 99% confidence level. So smaller MDP99 means better polarization sensitivity because that means the polarimeter can detect fainter polarization. And MDP99 can be calculated using this formula. And short, the MDP99 determined by the modulation factor and detection efficiency of the detectors and other parameters that depends on the observational condition. And modulation factor is modulation amplitude of the detector outputs when 100% polarized X-ray beam enter the detector. So to evaluate the polarization sensitivity, we measure the both modulation factor and detection efficiency. Today, I will focus on the measurement of the modulation factor. So we conducted the beam experiment at Spring 8 in Japan to measure the modulation factor of the CMOS sensor with the pixel size of 2.5 micrometer. After evaluating the sensor with nearly 100% polarized beam, we estimated the photon emission angle for each event and fit the corrected distribution of the angle with this function to determine the modulation factor. And we found that the modulation factor of the sensor is about 10% at the energies above the 10 keV. So this result shows that the CMOS sensor can use as X-ray polarimetry. And using the measured polarization factor and detection efficiency, we estimated the polarization sensitivity using the formula I showed in the previous slide. And the right figure shows the contour of the MDP99 on the plane of product of mirror effective area times the observing time versus the source flux. So this figure shows that for one cloud source observed for 2 millisecond with 100 centimeter square centimeter mirror, the MDP99 became about 5%. So these results shows that in order to realize the X-ray polarimetry using a fine pixel CMOS sensor, we need to develop a large area mirror system and or improve the polarization sensitivity of the sensor by using a finer pixel or thicker sensors. So please check my paper for more details. Let's move on to the last topic, the development of the Monte Carlo radiative transfer cooperation of relativistic effects. So as you know, there is recent progress in observatories providing new observational data. For instance, IXP enables X-ray polarimetry, and PRISM offer unprecedented high energy resolution spectrum. And in order to fully utilize these data and accurately analyzing them, process modeling is required. Such modeling is essential to study to address new science and get meaningful insights. And one of the examples is again the black hole corona. And as I said in the previous slide, the location of and structure of the corona and the accretion disk is still under debate. So, And most spectral analysis have assumed a lamppost model where the corona treated as a black hole above the points above the black hole. On the other hand, the recent polarization data from XPE suggests other models like sandwich model or truncated disk model where the corona extending along the disk. And understanding the corona structure is important for measuring the black hole spin or testing general relativity using the X-ray reflection spectrum of the black hole system. So to determine the true geometry, we need to find a model that can consistently explain both spectrum and polarization. And to compare the theoretical model with the observational data, we require a radiative transfer code that can calculate both polarization and spectrum from the same models. And since the corona and the accretion disk is located close to the black hole, so we also need to consider the general relativity. So that is the reason we are developing Monaco GL. Monaco GL is a photon tracking Monte Carlo radiative transfer code based on Monaco. Original Monaco did not include a GR effect, so we are incorporating the GR effect into Monaco. The Monaco GL will simulate the spatial data like spectrum polarization from the same model, and it will support various physical interactions and complex geometries. So the Monaco GL will bridge the gap between theoretical model and observational data. In Monte Carlo simulation, first photons are emitted from the same X-ray source, and these photons are tracked by solving the geodesic equation in a curved spacetime, and we account for the interaction between photons and materials along the path until the photon reaches the observer or fall into the black hole. And this simulation will enable spectral and polarization and timing analysis with arbitrary models. So let me explain about the development procedure of Monaco GR. Well, I said that we are incorporating GR effect into Monaco, but actual step involves the development of photon tracking code in square spacetime and integrate the process and materials on Monaco into it. So first, we develop the photon tracking code in curved spacetime, and we implement the computerization for electron. By adding the disk geometry, we can calculate the polarization from accretion disk, and incorporating corona geometry allow us to calculate the polarization from corona. And by adding the other processes and geometries from Monaco, we aim to achieve higher accuracy and flexibility. So far, we've already developed the photon tracking code and implemented computerization. And now I am working on a calculation of polarization from accretion disk. So I'd like to show you some simulation results. First, we calculated the photon trajectory and compare it with the analytical solution. As the right figure shows that the simulation results match the analytical solution even for the extremely thin value and when the photon emitted near the event horizon. We also calculated the line profile of the photon was emitted from the equatorial plane with the energy of 6.4 keV, and we calculated the observed photon energy. Our simulation successfully reproduced the red line model. And after implemented the computerization, we calculate the polarization from accretion disk. We assume that the disk emission follows the Novikov permissivity profile, and we also include the reflection of the disk. That means we include the returning radiation the photons are emitted from disk and bent by the strong gravity of the black hole and scattered again at the disk. The returning radiation is important for polarimetry because the polarization degree of the returning radiation is higher than that of the direct component. And our simulation results are generally aligned with the previous research, but some discrepancies are observed at higher energy and higher inclination angles. So now I am investigating the reason for these differences. And I plan to continue the verification of the code by calculating the polarization from disk and polarization from corona. And as application of the Monaco GL, I am planning to calculate the spectrum and polarization from the hot flow of the black hole system. And this model may include both seed photon from the accretion disk and hot flow via cyclotron or synchrotron process. And we aim to check if the model can reproduce the observed spectrum and polarization, if possible, the timing properties. So this is a summary for my talk. I've conducted the timing analysis of the iron line of CNA, and the result indicates that the reflector is likely to be a torus or more distant material. And we are developing X-ray parameter using a fine pixel CMOS sensor, and we evaluated the polarization sensitivity of the sensor. Now I am working on development of Monaco GR, Monte Carlo radiative transfer code, include GR effects, and I am planning to calculate and reproduce the spectrum and the polarization from the black hole accretion system. So if anyone interested in my research, I will be very happy to connect and discuss further. Thank you for your attention.
Thank you. Do you have any questions?
Hi, thanks. This was really exciting. I thought your approach with the top hat functions as a improved response or transfer function was really interesting. And do you plan to incorporate that into Monaco GR at some point? Like I think on one slide you mentioned timing. Is that something you've been looking into?
Yes, thank you. And yes, yeah, we are in the talk. In our CNA analysis, we are saying the transfer function, but the transfer function is reflect the geometry around the black holes, reflect geometry of the reflector. So by using the Monaco GL, we can calculate the transfer function of the system. So I think that is interesting. Intertopic that if the model can consistently explain timing properties and spectrum or other features. But CNA, in terms of CNA, the reflector is far from the black hole. So I think we don't need to consider the GR effect. Thank you.
Great talk. I was wondering about ciphers. So is this X-ray perimeter going to have like imaging capabilities? And if so, I know you're kind of still working on like the computer side and everything, but is there an estimate for what the angular resolution is?
Angular resolution. So we're using a fine pixel CMOS sensor. So yeah, originally we considered that we are thinking about the imaging by using the coded mask, because the pixel size of sensor is very fine, so it can achieve a higher angular resolution. Of course, it depends on the size of the code or the mask and the pattern of the mask and distance between the mask and the detector. But after we evaluate the polarization sensitivity, we realized that the coded mask cannot focus the photons onto this detector. So we need more large mirror systems. So the angular resolution of the imaging perimeter is will depend on the mirror, I think.
Thanks, Toshiya. Very interesting talk on a number of very interesting fronts. I wanted to just advertise for everybody that Toshiya is stationed in B102 for the next few weeks, in Cubicle B, I believe. But I had couple of questions also on CIFAR for you. So I wondered if you had looked at, or if you could comment on the energy dependence of the modulation factor. So you said 10% at, I think, 10 keV. If you say 5 keV or 20 keV, how much does that change?
Okay.
And I wondered if you foresee different CMOS developments like pixel size, detector thickness, or things that might potentially improve the modulation factor with any significance.
Okay, thank you for your question. First, about the energy dependence of the modulation factor, I can show you the picture of the. Yeah, this is the left figure is the energy dependence of the modulation factor, so it increases with energy, but on above the 15 keV or something, the modulation factor became flat. But this behavior is really complicated because it depends on the way to how to analyze this. How to analyze the data. So how to estimate the polarization angle and which event we use to estimate the polarization. So this is one example of one way that provide a maximum modulation factor from the way what I am trying, but it basically increases with the energy, but above the 10 or 15 keV, it's about 10%. And yes, also, we also measure the polarization sensitivity for the CMOS sensor with the 1.5 micrometer sensor, which is smaller than this because it's 2.5 micrometer. And please check my paper for the result. Okay, I'm sorry, I didn't prepare the result, but it actually improved the modulation factor, but the sensor was thinner detection layer. So in terms of the spec of polarization sensitivity, this sensor provided better quality.
Thanks.
Thank you. Any more questions? See no here. Okay, if not, let's thank Toshiya again. Okay. You just want to, so they can shift the dashboard. Okay, so while we set up, I introduce the second speaker. Sohyoun Yun-Cárcamo. She's a PhD candidate in physics at the University of Maryland, specializing in gamma ray astrophysics with the high altitude water challenge, also known as HAWC, Gamma Ray Observatory. And she's currently in her fourth year and she's on track for graduating in May 2025. In the initial years of her PhD, Sohyoun focused on testing and improving the performance of the HAWC reconstruction algorithms. These improvements allowed the observations of the Galactic Center and consequent analysis of for the confirmation of the PeVatron mission during her third year. Currently, she's dedicated to her dissertation and to the search for a dark matter signature in the Galactic Center. Today,
Yeah, at the end.
so maybe, okay, thank you. And today she's going to talk us about this observation of the Galactic Center PeVatron Beyond the TV with HAWC. Thank you, the floor is yours.
Okay, yeah, good afternoon, everyone. Thank you for having me here. I was invited to talk about this publication called Observation of the Galactic Center PeVatron Beyond 100 TeV with HAWC. It's in abject letters. And I'm gonna tell you everything important first, and then we're gonna go step by step. So in this work, we present the first detection of gamma rays with energies above 100 TeV from the Galactic Center using HAWC data. But now let me rephrase that. This is the first time we have gamma rays above 50 TeV from the Galactic Center, ever. These results suggest that the gamma rays that we are observing originate from interaction of protons from the central molecular zone and PeV protons that are freshly accelerated within the Galactic Center region. So you can see in the picture the central molecular zone, which is composed mainly of giant molecular clouds, so hydrogen, and we also have some stellar clusters. The results suggest that these protons from the clouds interact with the PeV protons that are accelerated by the PeVatron and produce a neutral pion, that indicate to gamma rays that we detect. So that's the main picture. But let's put all of this into context. So the cosmic ray spectrum has been measured and constructed over decades by different experiments, and it is widely believed that the cosmic rays with energies below the knee are accelerated within the galaxy. Now, we also know that these cosmic rays cannot be traced back to their origin because of their deflected trajectories. So instead, we use gamma rays, which are not deflected, and we can trace back to their origin directly. And there are many galactic particle accelerators that have been identified using gamma rays. However, we lack conclusive observational evidence of acceleration to PeV energies. So we detect cosmic rays with PeV energies. We know they are accelerated within our galaxy, but we don't know where. At least we don't know a source or a type of source that can account for all the flags that we detect. In this talk, we're gonna center on that part of the picture, the Galactic Center, and we're gonna use a ground-based detector called HAWC to analyze the observations of gamma rays. Now, we know that gamma rays do not penetrate the atmosphere. Instead, they strike in the upper atmosphere and they produce a shower of particles via pair production and bremsstrahlung. So we have this first gamma ray, and then we have electron positron, and then bremsstrahlung, and we have a shower of incoming particles that get to the ground. There are two main types of gamma ray detectors that we have on the ground. One of those is the water Cherenkov detector array, which basically detects the Cherenkov light emitted in the water by these secondary particles produced in the shower. And these are characterized for having a large field of view, high duty cycle. There are 24 hours working every day, and they're also very sensitive to high energy gamma rays. So these high energy gamma rays of hundreds of TeV, they produce these big showers, so you need a very large effective area to detect them. The other type of ground-based gamma ray detectors are the IACTs, Imaging Atmosphere Cherenkov Telescopes. Instead of using water, these trace the Cherenkov light in the atmosphere. You can see in the picture, these are pointing instruments, so they have a great angular resolution, but they can only operate in moonless clear night sky. So their duty cycle is very short. And we have those two examples, HAWC for the water Cherenkov detector array and HESS for the IACT. In particular, we're going to talk about the high altitude water Cherenkov gamma ray observatory. You can see the size of the tanks. There's a ME for tank size scale. This detector is located on the flanks of the Sierra Negra volcano in Mexico at an altitude of 4,000 meters. The main array is composed of 300 of those huge tanks, and our sensitivity is between hundreds of GeV to hundreds of TeV. And HAWC surface the sky, 2/3 of the sky daily. Now, I said that gamma rays do not penetrate the atmosphere, so how do we actually detect them? You can see in the diagram an incoming gamma ray and the extensive air shower. The front, the kind of curved and arrives to the detector and leaves a footprint. So we have the arrival time and the charge of the particles in each PMT, and only with that information we reconstruct if the shower was coming from a gamma ray or a cosmic ray, because cosmic rays also produce showers. We reconstruct the direction of the primary gamma ray, and we also estimate the energy of the primary gamma ray. This is easier to do when the shower comes from right above. Everything's symmetric, so it's easier for our reconstruction algorithms. But when the shower comes from a very tilted direction, everything becomes very difficult. In fact, the Galactic Center wasn't in our field of view until last year. Now, that sounds weird because the sky didn't rearrange itself. What happened is that we improved our reconstruction algorithms, which is what I worked on the first years of my PhD. So you can see a piece of the sky. The pass 4 is what we call a reconstruction algorithm before the improvement, and pass 5 is with improvement. So you can see it's kind of like when you take your glasses off and you put them on, you can see the difference in the angular resolution. And the green arrows are pointing to the Galactic Center. So you can see before there was kind of like a blob, but not at the center. And after, we can see significance at the Galactic Center. In particular, the performance improved for high zenith angles, so showers that come from larger angles larger than 35, 37 degrees zenith and 70 TeV. You can take that paper where I characterized and showed how we improve the reconstruction algorithms. But the important thing is that for showers that come from the direction of the Galactic Center, we improve by a factor of 4 both our angular resolution and our background rejection. Thus, using over 2,500 days of data, we detect gamma rays from the Galactic Center with a maximum significance of 6.5 sigma above the background. Now, I'm going to show you the results. So that is a kind of zoom in of the big map that I showed you before. That's a significance map. That's how our data looks like using all the energy range that we can see. The dashed line circle is a extension upper limit at the 68% of confidence level, although our best fit is a point source with a power law. Previous results from IECTs reached a maximum energy of 40 TeV. However, we go over 100 TeV. So these IECTs, the type of detectors that I showed you before, they suggested that there was a PeVatron at the Galactic Center, but they didn't reach the 100 TeV. So now we can confirm that in fact we get gamma rays with energies above 100 TeV in the Galactic Center. Furthermore, we can already discover the electronic origin of these gamma rays. So to produce gamma rays with energies above 100 TeV, we can have the leptonic origin, in which via inverse Compton scattering, these gamma rays get accelerated to energies of 100 TeV, or the hadronic origin. But what happens in this medium here, where we have very large magnetic fields and a lot of material, is that the electrons cool down very fast. So even if we assume the extreme case of ballistic movement, at the speed of light, the electrons can travel only 5 parsecs before they lose all the energy, so they cannot interact and produce the gamma rays. For scale, you can see that 1 degree is approximately 150 parsecs. Now, our best fit model, which is a dashed line circle, it's coincident with 2 Hess point sources. So this type of detector that has very great angular resolution can identify 2-point sources, but we cannot. Although our model is coincident with their Pac-Man-shaped diffuse emission region that you may or may not remember from the Nature paper, where they first suggested the PeVatron of the Galactic Center. And there are also other sources that are nearby, but we cannot detect. So for the curious, we don't know what the blob is. There are no known sources there, and we don't see it above 5 sigma, so we cannot claim discovery. And the SNR that is at the center, its flux is below our sensitivity, so we can also not see it. Okay. So I told you that our best fit model is coincident with these 2-point sources and the diffuse emission region. So here I'm comparing the spectra. The pink one is our best fit model, best fit spectra, and the cyan and green are the spectrum of the Sagittarius A star and the other unidentified source, which we call the arc. We cannot resolve these sources because of our angular resolution, but we can extrapolate the spectra and see what is the contribution to the overall flux that we see. And here I'm showing the significance map, where I take the original significance map and we subtract the excess of the point sources from our data to see what it looks like. So if we could subtract the contribution of those 2-point sources, this is what it would look like. And I'm also showing the contours of carbon monosulfide line emission, which helps tracing the gas that is there. So you can see that the correlation happens mostly at the center, which is already giving us hints of the interaction that occurs there with the gas and the PeVatron. So to be even more explicit, what we do is we subtract the spectra of the 2-point sources from our result, and we get something like the purple spectra. And you can see that the spectrum continues to above 100 TeV without evidence of a curve. So this is very likely galactic center diffuse emission from PeV protons interacting with the molecular clouds. And a small contribution, there must also be some unresolved sources. And for comparison, I'm also including the diffuse flux points from the Pac-Man shaped region that it was mostly or almost completely overlapped with our best fit model. And you can see that they are in agreement with the uncertainties. Okay. Now, we already talked about how the electronic origin via inverse Compton is disfavored because of the efficiency synchrotron cooling. So the electrons cannot travel very far, so they do not interact, and they cannot account for the gamma ray emission that we see. For the protons, it's actually the opposite. So the protons have a very long cooling time, so long that we can dismiss it. We do not care about their cooling time. But we have the opposite problem. So the protons can escape from this region in 100 years. But luckily, we have here the magnetic field and a ton of material that can trap the protons in the galactic center. And the only explanation left for how we're getting this gamma ray emission from protons if they escape so fast is that the proton sources are very young, or they're injecting protons into the central molecular zone in a recent burst. But this time is too short. It's very small compared to the age of the galaxy, for example. So the only explanation is that we have one or more sources that are quasi-continuously accelerating and injecting high-energy protons into the central molecular zone at rates that exceed the escape rate. We also made some consistency checks. So we calculated the energy density of cosmic ray protons using our measurement of the gamma ray flux above 10 TeV, and we obtained that this energy density is 8 times larger than the local measurement by the AMS. And we also checked that the total vector of protons with energies above 100 TeV is compatible with the previous measurements by HAWC. So in summary, we attribute the ultra-high energy gamma rays to the freshly accelerated protons cosmic rays from the local accelerators within the Galactic Center region, which are continuously injecting protons with PeV energies. HAWC confirms then the suggestion made by lower energy observations of the Galactic Center diffuse emission, but we cannot resolve the specific PeVatron source. Although we have been coming years as CTA and SWGO, which are observatories that are going to be in the southern hemisphere, they could better constrain models of the central molecular zone, so we could maybe point to the PeVatron source. And that's it. I'm graduating soon and I'm looking for postdoc positions. Thank you.
Thank you. That was really exciting. Thanks. Any questions from here? I have one. Do you think you can combine in the future this observation from HAWC with the Fermi lattice to constrain what these sources are? So there is a long 10 years old encounters from Fermi lattice on this millisecond pulsars versus the dark matter. And also, the second question is, could this source diffuse all over the galaxy, contribute significantly to the isotropic cosmic ray spectrum at this energy? Because now in the last few years we saw the problem that supernova and shocks might not be sufficient to power the spectrum beyond a few tens of TeV. So could this source also contribute to that?
Yes.
First questions.
Yes. So for the first question, that's actually my proposal for an MPP that I applied. So that's my postdoc proposal to work combining Fermi-Lat data and HAWC data to constrain the Galactic Center access, to see what, maybe there's a combination of millisecond pulsars or dark matter, or maybe it's just one of them. It is a proposal that I have. So I think it is possible. And for the second question, the Nature paper that has published, they made the calculations, and the Galactic Center PeVatron doesn't account for all the flags that we detect, but it can account for most of it. We also have other sources that are PeVatrons that we recently published from HAWC, so it could be some big contribution from the center, from the supermassive black hole, and other small contributions here and there in the galaxy.
Okay, so let's hope that your project will happen.
Really fascinating talk. I was curious if you had sort of a capacity to build an infinitely large HAWC. I assume you could shrink down the sizes of those of your localization pretty effectively. But at some point, I expect you have magnetic turbulence from the galaxy sort of deflecting the proton paths, so that it sort of fuzzes things out at some size scale that has to do with turbulence in the galaxy. Is that very small arc-second scale compared to 10 arc-minute scale, or what sort of level does that start impeding things?
Okay, so for the first part of the question, we have in fact some smaller tanks that are outside of the main array and that are more spread out. With that, we hope to improve even more our reconstruction algorithms. You can detect bigger showers, so higher energies, and you can also improve the angular resolution because you can account for all the features in the footprint of the shower. So that could improve a lot this. And for the second part, I don't know if that's in the scale that they can affect our. It's a very complicated region because there's also unresolved emission from sources that no one can see. So I'm not sure. Not sure that it's in a scale that we can resolve.
Yeah, probably the two ones are just local Galactic Center, so it will be still coming through there.
Nice talk.
Thank you.
Where can one find a catalog or list of all sources that HAWC has detected? We had a talk here a few months ago, and included in the talk was the HAWC detection of a black hole X-ray binary, which is a totally new class. And I'm sorry, I'm not remembering which object this was. I could go and look it up. But is there on the website a catalog of what has been seen?
So
This would be a very interesting example that could relate to the Galactic Center.
yes.
Some reasons that I could tell you about.
Oh yeah, I'd be interested in that. Okay, so we have a catalog, but it's from the past reconstruction algorithm. So it hasn't been updated in a while. We have someone working on it right now. So it should be published soon. In the webpage, we only have the news of the recently published papers, but not like a list of the sources yet. So yeah, I don't think that helps you much, but we don't have a catalog yet with improved reconstruction algorithms.
Thank you.
Any more questions? No here. Let's check upstairs. Okay. No, I see no. So if not, let's thank Sohyoun and both speakers of today. And we'll see you next week. Let's